So the next set of formulas that we're going to cover are referred to as semi-perimeter formulas. The perimeter of a triangle, that's the sum of the length of the sides. So if you have side A, B, and C, the perimeter is A plus B plus C, and the semi-perimeter is half of that, so that's A plus B plus C divided by 2. Semi, as you know from other words, means half. And these semi-perimeter formulas, they're quite interesting because what they do is, and actually we'll denote the semi-perimeter by S. So what the semi-perimeter formulas buy you is they give you the sine of alpha over 2, the sine of beta over 2, and the sine of gamma over 2 as a function of the semi-perimeter and the length of the sides. So here you basically have the semi-perimeter S and the sides A, B, C, and here on the left-hand side you have something that involves angles. So a very typical kind of problem is also to go from the angles to finding the semi-perimeter, or vice versa, if you know something about the three angles, the three sides to get the angles. So let's try and prove one of these formulas, and I'm going to look at just the first one. So here what we're going to do is we'll try to prove this formula, and then the others are very similar. In fact, again, you can see the very regular structure in the formulas here. To go from formula 1 to 2, alpha becomes beta, A becomes B, B becomes C, C becomes A, and so on. So once you know one, you know the others. So for the proof, what we're going to do is, first of all, we have a half in that expression on the left-hand side, so we'll use the half angle formula. And we have that cosine of alpha is equal to 1 minus sine squared alpha over 2. So that's good because we have that sine alpha over 2 in here. We have a square. We can probably turn it into a square root. So this is probably a good formula to use here. And let's also put the angles, beta, gamma, and alpha. On the other hand, we also have the law of cosines that tells us that cosine of alpha is b squared plus c squared minus a squared divided by 2bc. So if we take those two and we eliminate cosine of alpha, what we get is that 2 times sine squared of alpha over 2, so there's that 1 here, but I'm going to bring that to the other side, is 1, that's at 1, minus b squared plus c squared minus a squared divided by 2bc. From this point on, we're going to have to do a bit of algebra on the right hand side, but we actually are almost there. We almost have that formula. So let's bring this on the same denominator. Then what I get is 2bc minus b squared minus c squared plus a squared, divided by 2bc. And now I see something interesting in there. I have 2bc minus b squared minus c squared. If you think a little bit about the formulas that you know from algebra, you have something that looks like x squared plus, not x squared plus y squared, but you know that x plus y squared is equal to x squared plus 2xy plus y squared. So here we have the same thing. We're going to use b minus c squared is b squared plus c squared minus 2bc. So that then gives us a squared minus b plus c squared divided by 2bc. Sorry, this should be a minus here because I have the same signs here. And now I can use another formula from basic algebra. You also know if you have x squared, so I'm putting them on top of the slides because it's an easy way to get some space. X squared minus y squared is equal to x minus y times x plus y. So this is formula 1. I use that here. Now I'm going to use formula 2 to write this expression on top as a minus b minus c times a plus b minus c. So that's number 2, and that's divided by 2bc. So I can make that a bit nicer, get rid of some of those parentheses by writing it as a minus b plus c, a plus b minus c divided by 2bc. And now, in order to relate that to the semiperimeter, I'm going to create some space here, so this is getting quite a full slide. But let's look a bit at what I know about the semiperimeter. So I know it's a plus b plus c divided by 2. So 2 times s is a plus b plus c. And now here I don't have a plus b plus c. I have a minus b plus c. So what I can do is I can subtract 2b from both sides to get 2s minus 2b is a minus b plus c. Likewise, here I have a plus b minus c, so I can also form that expression by subtracting 2c from a plus b plus c to get a plus b minus c. So then if I continue over here on the right hand side, what that gives me is 2 times s minus 2 times b, 2 times s minus 2 times c divided by 2bc. And now if I get rid of some of these factors of 2, I can write this as 2 times s minus b, s minus c divided by b times c. So now let's have a look at where we started. We started with this. 2 times sine alpha over 2 squared, and we end up with this. So again here the factors of 2 will cancel, so this 2 will eventually cancel against that 2, and what we have left is sine squared alpha over 2 is s minus b, s minus c divided by bc. And now if I take the square root, that's equivalent to sine alpha over 2 equal to square root of s minus b, s minus c divided by bc. So that's exactly the first semiperimeter formula. So now there's a few more formulas that are similar. I'm not going to work through the entire proof because it's similar in terms of the approach. So there's a semiperimeter formula for the cosine, and it's given here. And once again, it relates something that has to do with the semiperimeter and the sides on the right-hand side, and then the angles and trigonometric formulas on the left-hand side. So for the cosine formula, what we're going to do, and I will sketch the approach, but not all the steps in detail. So we'll start again from the half angle formula. And for that we have cosine alpha is equal to 2 times cosine squared alpha minus 1. So this is the other half angle formula. And at the same time, we again know that the cosine formula, the law of the cosines tells me that cosine alpha is b squared plus c squared minus a squared divided by 2bc. So from that I have that cosine squared alpha over 2 times that, let's say, is 1 plus b squared plus c squared minus a squared divided by 2bc. So I'm going to let you work through this by yourself. So if you do this algebra, just like we did on the last slide, then what you will end up at the end of the day is that this is equal to 2 times s minus a divided by bc, and then again taking the square root we get that cosine alpha over 2 is square root of s minus a over bc, and that gives us the first of these expressions. The others are exactly the same, they have the same structure, so you just have to replace alpha becomes beta, a becomes b, b becomes c, and c becomes a. And then there's a last set of formulas for tan of the half angle in function of the semiperimeter and the length of the sides. And here the derivation just follows from the definition of sine and cosine. So we can start on 1. You can write this as sine alpha over 2 cosine alpha over 2, and then if you look back at your formulas, then what you get is that this is equal to big fraction s minus b s minus c divided by bc, the square root of this whole thing, and then for the cosine you have s minus a divided by bc and the square root of that whole thing. And now you see the denominators cancel, bc here, and we can write this as a big square root, put the equal sign a bit lower, a big square root of s minus b, s minus c divided by s minus a. So that gives us our first formula, this one right here. Okay. So then moving on, we have some closely related formulas, but that have to do with areas, and sometimes you see these in the literature or in engineering books referred to as Heron's formula. So Heron was a mathematician from ancient Greece who apparently found one of these formulas. And the interesting thing here is if you look on the right hand side, here now instead of semiperimeters you have areas. and on the right you have, on the left, sorry, you have angles. So that's for these three formulas. And actually, Heron's formula, which I just skipped over, that's this one right here, which gives you the area of the triangle as a function of the semiperimeters and the length of the sides. So this is also a useful formula because sometimes you're given an arbitrary triangle and you have to say something about the area, but you only have the sides. Let's say you're putting tiles in your bathroom, and your bathroom is an irregular triangle, and you want to know how many square meters your bathroom is or something like that. Then you can measure the sides, plug it into Heron's formula, and get the area. It would normally be quite difficult to do that otherwise. So let's have a quick look at the proof of Heron's formula. And for that, I'm going to draw a triangle like we're used to by now, alpha, beta, and gamma, A, B, C. And what we're going to do is, we've done this a couple of times, we like right triangles, so we'll make this into a right triangle by having a perpendicular here. And we'll call this length H. So what do we know about the triangle? Well, we can already write down the area. So the area of a triangle is the length of the base times the length of the height, h, divided by 2. And we don't really like that h, so we can use a little bit of trigonometry here to write. We know that h divided by b is sine alpha, so that's in triangle 1 here. And we can use that on the right hand side here to write this as c times b times sine alpha divided by 2. And now if you bring the c's and the b's and the 2 to the other side, you get already that sine alpha is 2 times the area divided by c over b, and that's one of our formulas here. That's this formula. And the others are very similar. So now let's keep moving on, and let's see if we can get to Heron's formula. What I'm going to do now is I'm going to take this expression here, and I'm going to work it out a bit more. So here we want to get at Heron. So we know area is BC over 2 sine alpha. Now I'm going to do something that looks a bit strange. I'm going to write that sine alpha as 2 times sine alpha over 2 cosine alpha over 2. So I get BC over 2 to sine alpha over 2 cosine alpha over 2. I see that these factors cancel. Now I'm in a good position because now I can use the semiperimeter formulas. So I can write this as, and let me underline it so that you know which is which. So sine alpha over 2, I just found an expression for that. I know that's the square root of s minus b, s minus c, square root bc. So that's sine alpha. And cosine alpha over 2, that's, I have to look at my notes, s minus a divided by bc and the square root of that. And you can see what happens here. So I have a bc in the denominator, I have a square root of bc here, I have a square root of bc here. So this cancels against this and this. And now if I bring everything under the square root sign, what I end up with is s minus a, s minus b, s minus c, all underneath the square root. And that gives me precisely Heron's formula. Just in a color, like so, Heron's formula as we had it here.